Hey everybody. We are going to continue with waves and sound specifically. This week, I actually made an entire different video and realized it just wasn't going to work. And I wanted to do things related to the Slinky Lab, where we can study the conceptual aspects of waves. And then I just made a video about standing waves on strings and in air, and it's just not working with remote instruction. So we're going to go with the more standard and just apply some math to sound waves. But we need to talk about the two different types of waves. This is something you should know, the difference between longitudinal and transverse waves. There are two types of waves. Longitudinal waves are when the particles of the wave move parallel to the direction the wave moves. So they move parallel or along with the wave. So the particles of the wave will move with the wave. This will be a sound wave, and that's basically the wave we're going to be focusing on for the rest of this topic. The transverse wave is usually more focused on with the slinky, and unfortunately, we can't do slinky labs unless you all have slinkies and we can try it together. But anyway, transverse waves are when the particles of the wave move perpendicular to the direction the wave moves. Good example of this is actually a wave on a string. If you've ever seen a wave on a string, or if you've ever used those heavy ropes that you shake up and down, you're shaking up and down, but the wave is moving away from you. So the particles of the wave go up and down, but the wave itself moves away from you. Speaking of that, the wave, if you've ever done it, which I hope you have, when you stand up and lift your arms and sit back down, your body's going up and down, but the wave goes side to side. And of course, there's also ocean waves, which are pretty similar to transverse waves. Not quite, but when you're sitting on the surface of the water, if you're just sitting there and a wave comes by, you go up and down, but the wave goes side to side underneath you. So those are the two types of waves. I am going to recommend that you're going to pause the video and you're going to watch two other YouTube videos. One is showing you an animation of a longitudinal versus a transverse wave. It's a good animation. It does help you to visualize it. And then the other is what is sound. I show it every year. It's a great video. It's a cartoon of what sound waves look like and how they propagate through the air. So please pause this video and check those two out, and then come on back. All right, welcome back. Hopefully those videos were helpful. And today we're just going to really focus on figuring out the speed of a wave in a string and the speed of sound in air. So normally what we'd be doing in class is we could have a guitar. If anybody's got a guitar or any stringed instrument, we're going to talk about a standing wave, kind of like a jump rope wave, that is vibrating from end to end. And I just want anybody who knows that plays a musical instrument that we are skipping everything to do with harmonics and things like that on strings and the different actual vibrations that you would see on the string, because it's just kind of difficult. And honestly, you'd probably be bored more than now listening to me trying to explain all these pictures to you. But we're skipping kind of the musical part of this topic, and I apologize for that, but it is what it is. So here's a wave on a string. And anybody that plays a musical instrument, you should probably know some of the things that might affect the velocity of a wave on a string. You could always pause the video for a second and just try to think, what would affect the velocity of a wave on a string? And now you're back, or you just waited for that moment. But hopefully you were thinking, like, if you think about a stringed instrument, there are different thicknesses. So maybe the mass of the string would have an effect on the velocity. Also the tension when you're tuning, definitely. And the only other thing that you can really change is the length of the string. And there's various ways to do that. So those are three things. We want to come up with an expression for the velocity of the wave on the string. So I guess what normally do is say if the mass gets bigger, what do you think happens to the velocity? If the tension gets bigger, what do you think happens to the velocity, and so on. So if you'd like to, you could think about that for a second and pause the video and think, what happens if I increase each of those? What do you think would happen to the velocity of the wave? And now you're back, or you didn't go anywhere. But this is why I miss class discussions. You usually hash it out on your own. But what we end up with is something you should be aware of. V equals F lambda. For anybody that has tuned a string instrument, you know that if you increase the tension, the frequency or pitch you hear goes up, but you have not changed the wavelength. The wavelength is still from node to node, from end to end of the string. But if the frequency goes up, the velocity goes up, because this will be staying the same. Okay. So if you've ever tuned a string instrument, you know that as a tension goes up, the frequency goes up. And therefore, the frequency goes up, the velocity must be going up. So there must be some kind of relationship where the tension is in the numerator. Also, for those that know, keeping the thicker strings in mind, those thicker strings play lower notes. They have a lower frequency. Lower frequency means lower velocity. And therefore, as the mass goes up, velocity goes down. That's in the denominator. And then as it turns out, if we keep the frequency the same, if we were able to do that, if we keep the frequency the same and increase the length, which will lead to a larger wavelength, the velocity increases as well. So technically, I know that should be in the numerator because they're directly related, not inversely related, but it actually goes in the denominator, and it's known as a mass to length ratio. That's kind of weird, I know. And then all of this is under a square root symbol. So this is technically the expression for the velocity of a wave based on its tension and mass to length ratio. It is also written as velocity as a square root of tension, force of tension, over mu. I know, it's not coefficient of friction. Mu is just m over L. So I don't care which way you look at it. Some people, and this is basically just a substitute and solve kind of expression. There's nothing tricky, no need to do a sample problem. But some people have trouble with the math because of the radical and the fraction within the fraction. If you're uncomfortable with that, solve for the mass to length ratio first, then sub it in as ft over mu. Or if given V and tension, solve for mu, and then use the mu to solve for M or L, mass or length. If you're not uncomfortable with it, fine. Then some people look at it as V equals the square root of Ft times they bring the length up and they leave the mass on the bottom. However you do it, it is simply a substitute and solve. Hopefully, though, you make connections, though, with between the tension and the speed, the mass and the speed, and the length and the speed. So that's a pretty simple expression to calculate the speed of a wave on a string. Now, speed of sound in air, there's not much to be said about that. It's honestly, it's just an expression. It's V equals 331 meters per second plus 0.6. Now, these are units. Meters per second degree Celsius. That's a weird set of units. Meters per second degree Celsius times T, but this is temperature. Sorry about that, but that's how it is. So this is the velocity of sound in air. And this is, the one on the left is the velocity of a wave on a string. So, the velocity of sound in air, hopefully, again, we normally have a conversation about what happens to gas molecules as they get hotter. Hopefully you know that they get faster. You start moving around and They're full of energy. Therefore, the time it takes for them to collide decreases. Therefore, the sound can propagate faster. That's why as the temperature increases, the velocity of sound increases. So as a simple sample problem, because some people screw up these units and there's nothing to screw up, let's say we go outside right now and it's room temperature-ish, 21 degrees Celsius. So how fast is the speed of sound? That's really not too tough. 331 meters per second plus 0.6 meters per second degrees Celsius times 21 degrees Celsius. So the degrees Celsius is what divides out. Those are units. And then you're just left with meters per second. Again, meters per second degrees Celsius is units. Every year, people are like, oh, that's a new equation I should use. No, it's not. It's just units. And then after that, you're just subbing into a calculator. So we'd get E equals 331 meters per second plus 0.6 times that is, 12.6, almost lost my mind there, meters per second, giving us a total speed of 343.6 meters per second. And that would be the speed of sound in air. Something to keep in mind for both of these expressions, because we haven't learned anything else. The velocity of the wave is constant. And if that's the case, then we can use V equals delta D over delta T to try and find distances traveled. As with the last homework, if you were to shout, and that sound wave, so here's you shouting, goes out. It rebounds off of something and you hear an echo. Well, if the time it takes is 10 seconds to hear echo, then it's only a 5-second trip to get to the wall. Right? It'd be 5 seconds there, 5 seconds back. That was the most missed thing on the homework, as some of you missed that, but hopefully it's not a big deal now. So basically what we're getting out of this video is two new expressions, one for the velocity of a wave on a string and one for the velocity of sound in air. They are pretty much substitute and solve kind of expressions. And if you have any questions about this or the homework, you know to email me or stop by for office hours, and I'd be happy to help you. But don't hesitate. Some of you are handing in homework that's like incomplete or I don't know. That's not really acceptable and doesn't have much dignity. I'm here for office hours. Just email me a question. I'll get back to you. It takes like 5 minutes. No big deal. Hope you're doing all right. Miss you all. Take care.